somewhere beneath the South China Sea, 40 meters below the surface of one of the world's busiest shipping lanes. For lanes of motor traffic move silently through a tunnel that should not exist. The Hong Kong-Zhuhai Macau Bridge is the longest sea crossing ever built. 55-kilometer structure that required China to solve engineering problems for which no precedent existed anywhere on Earth. What you are about to see is not just a bridge, it is a complete reimagination of what human beings can do to the ocean floor. Before October 24, 2018, crossing the Pearl River estuary from Hong Kong to Zhuhai took 3 hours by ferry or a lengthy road detour of several hundred kilometers. That journey is now 30 minutes. The Hong Kong-Zhuhai Macau Bridge, HCMB, connects 3 of China's most economically significant territories across the waters of Lingding Bay in the South China Sea. It is simultaneously a road bridge, an undersea tunnel, and to artificial islands built from nothing in the middle of the ocean, all engineered as a single, continuous structure. The total investment reached approximately 126.9 billion RMB, roughly $20 billion USD. Construction began in December 2009 and ran for 9 years, absorbing more than 400,000 tons of steel, enough to build 60 Eiffel Towers from scratch. The bridge was designed to last 120 years. It was designed to survive a magnitude 8 earthquake. It was designed to absorb a direct collision from a 300,000-ton supertanker without structural failure. And at the center of it, all buried in the dark beneath the shipping lanes, sits a tunnel that took the entire global engineering community's attention to design. To understand how this crossing was built, we begin where the water is deepest. The Pearl River estuary is not empty water. At the point where the HCMB crosses the main Tongnu and Lingding shipping channels, supertankers up to 300,000 deadweight tons navigate continuously. Vessels so large that no bridge with sufficient clearance could be economically built above them. The solution was to go under. But the seabed at the tunnel crossing sits at water depths up to 45 meters, with a further 23 meters of backfill required above the tunnel crown, meaning the tunnel structure would need to be positioned more than 40 meters below the sea surface, in soft marine sediments, in a high seismic zone. With an active fairway directly overhead, the engineering contractor engaged for the tunnel, a design-build joint venture led by CCCC, China's state construction giant, with technical input from Danish firm COWI. Spent years on foundation surveys alone. The seabed conditions were inconsistent, pockets of soft silt interspersed with harder strata, varying from meter to meter across a 6-kilometer corridor. At peak construction, more than 14,000 workers were on site across the full project, spread across the bridge sections, the tunnel fabrication yard, and the 2 artificial island worksites. The project operated 24 hours a day, with construction vessels numbering in the hundreds working simultaneously across the estuary. The scope defied comparison. The construction footprint, from bridge anchorage to bridge anchorage, covered more than 50 kilometers of open sea. Stage 1. Artificial island construction. Steel cylinder piling. Tunnel cannot begin at the water's edge. It must transition from the open bridge structure to the submerged tube somewhere in the middle of the bay, and that transition requires solid ground where no solid ground exists. To artificial islands are constructed at the tunnel portals, each covering approximately 100,000 square meters, roughly the footprint of 14 football pitches, in 8 to 10 meters of open water. The original construction proposal would have required 3 years of conventional reclamation dredging per island. The engineering team rejected it. Instead, a novel deep insert steel cylinder piling method is developed specifically for this project. 120 large diameter steel cylinders, each 22 meters in diameter and up to 55 meters long, are driven vertically into the seabed using vibratory hammers mounted on custom marine cranes. The cylinders interlock to form a closed cofferdam ring around each island's perimeter. The interior is then filled with sand and compacted. Using this method, both artificial islands are formed in just 6 months. The original timeline had been 3 years per island. Stage 2. Seabed dredging and trench preparation. Before a single tunnel element can be placed, the seabed along the 6-kilometer tunnel alignment must be excavated to precise tolerance and kept that way. Despite continuous tidal sediment transport, specialized dredging vessels cut a trench along the tunnel center line, removing seabed material to the design depth. The trench bottom is then leveled with a gravel bed, the platform on which each tunnel element will ultimately rest. The leveling tolerance for the gravel foundation is extraordinary. The entire contact surface must be flat to within 4 centimeters across an area of 8,000 square meters per tunnel element. This work is performed at water depths up to 50 meters, using deep water survey systems and high accuracy dredging equipment developed specifically for this project at a reported cost of nearly 3 billion Chinese yuan. Sedimentation, the continuous rain of fine particles settling from the water column, threatens to undo the leveling work at every tide cycle. Sedimentation monitoring and removal runs continuously throughout the placement phase. Stage 3. Tunnel element fabrication. The tunnel itself is not bored. It is built on land, floated into position, and sunk. The HCMB tunnel consists of 33 individual rectangular concrete elements. Each element is 180 meters long, 38 meters wide, and 11.4 meters high. A concrete box the size of a 60-story skyscraper laid on its side. Each element weighs 76,000 tons. The elements are fabricated at a dedicated casting yard in Zhuhai using C45 high-performance concrete, a mix specified for the aggressive marine environment and the 120-year design life requirement. Steel reinforcement is dense. Waterproofing membranes are applied to the exterior surfaces. Each completed element is fitted with bulkheads at both ends to allow it to float during transport. Ballast tanks within the element structure allow controlled dewatering and rewatering, the mechanism by which each 76,000-ton box is eventually sunk to the seabed with precision. Stage 4. Open ocean element towing and immersion. This is the stage that no engineering textbook had an answer for at the scale required. Each 76,000-ton tunnel element must be towed from the casting yard, navigated through active shipping channels, positioned over the trench to millimeter-level accuracy, and sunk to the seabed in a controlled, fully monitored descent. While the Pearl River's tidal currents, surface winds, and passing vessel traffic work against the operation at every moment, towing is performed by a fleet of tugs working in coordinated formation. Each element is ballasted to a slightly positive buoyancy, barely floating, to allow precise positioning at the surface before immersion begins. Once positioned above the trench using GPS and acoustic transponders, a fully automatic immersion system, another technology developed specifically for this project, takes control. Ballast tanks are flooded in sequence. The element descends, guided by a system that monitors its position and attitude in real time and makes continuous corrections. The landing tolerance on the gravel bed, 4 centimeters, for a 76,000-ton structure descending through 45 meters of seawater with tidal current present. All 33 elements are installed successfully. The HCMB tunnel wins the ITA Tunneling Award for Major Project of the Year in 2018. Stage 5. Vehicle exhaust from a 6.7-kilometer enclosed tube within defined time limits. A technical requirement with no margin for underperformance. The camera pulls back, now, past the ventilation stacks on the artificial island portal, across the sweep of the main bridge, out over the expanse of the Pearl River estuary, and from altitude. The full structure is visible for the first time. 55 kilometers of human engineering, lying in a line across the South China Sea, as if someone had simply decided to connect to points that the ocean had placed 3 hours apart. The Greater Bay Area that the HCMB now serves as home to more than 86 million people and generates over 1.6 trillion United States dollars in annual economic output, comparable to a G7 nation economy anchored to a single river delta. The bridge has not merely reduced travel time, it collapses the economic geography of southern China, pulling the manufacturing corridors of the Pearl River Delta into the orbit of Hong Kong's financial infrastructure and Macau's tourism economy in a way that was physically impossible before October 2018. The structure was built to survive for 120 years. It was designed to absorb earthquakes, supertanker strikes, and Category 5 typhoons. It was engineered in conditions, depth, current, sediment, seismicity, that had no established construction playbook. At the beginning of this film, a tunnel existed beneath the South China Sea that should not have been possible to build. What the Hong Kong-Zhuhai Macau Bridge actually demonstrates is that when a nation decides a thing must exist and applies sufficient engineering intelligence and construction resource to the problem, the ocean does not get a vote.